And see, when I get 3 hours of sleep, it really messes me up for a few days. Whereas you guys, 3 hours of sleep is like, oh, that was a lot of sleep last night. So it will catch up with you. It does. So anyway, we were talking about process scheduling. Another really interesting topic because there's so many interesting approaches that one can take, and you have these very common considerations that you have to deal with. Like say here, running process is blocked or suspended or terminated. We need to decide who gets the CPU next, and we need to make that decision in a way that preserves certain characteristics of our overall system, so that the user, when the user types, the system appears to be responsive. Okay. One of the things that I hated about Windows, this is just like a total detour, but when Windows would start, they would like show the desktop, and then they would take a while to show all the icons and show everything because they're still loading stuff. And it's like, why are you showing me a desktop when I can't interact with it yet? This is really a bad usability approach. So anyway, we'd want our system to be responsive and so forth. And we need scheduling to be fast so that we don't waste a lot of time scheduling. We'd rather use that time to compute. Also, context switches are slow. I mentioned this before. They tend to take on the order of 5 to 10 microseconds, which, if you remember our timings from assignment 5, our little lookups on our multi-map were like on the order of tenths of microseconds. So you can see, wow, context switch is a lot of time. So here are some of the details of what happens in the context switch. We'll talk about a few more of them as we get into the last topic that we'll broach today. But we have some hardware exceptional control flow that occurs. So the process is executing. It has a CPU. It has to be interrupted somehow. We switch to the kernel. So we have protection level change. We have a check to see if that's even allowed. We probably will change stack. And like I say here, we also change what data segment we're using because we're going into the kernel as well. There's certain things that are just a characteristic of switching protection levels on IA32, which is pretty representative of other operating or other hardware as well. So the kernel has to save the process control block. So it has to update the context in the process control block. It has to pull all those things out. Just a little bit of memory access that has to go on. Then it has to run the scheduler. Okay, and like I say here, hopefully this is quick. So it picks another process to start running again. This is more memory accesses, so maybe, hopefully not cache misses and so forth. And then it has to restore the other process's context, and this is where we may actually start generating a lot of cache misses. This is kind of the same as compulsory misses when we were talking about hardware caches, because the other process wasn't running, the cache didn't have its data in there if the previous process was using a lot of memory. And so in that situation, we're going to have a lot of compulsory misses because we're going to be accessing things that aren't in the cache. So you can see that context switches can be kind of expensive. Okay. So this is why they're so expensive, and this is why we like to avoid them. They're definitely not free. Don't ever imagine that they're free. Just like, well, I mean, the way that I would say it is that processes impose an overhead, threads within a process frequently impose an overhead, and the increased frequency of context switches is a major aspect of it. Okay, so those are sort of the things that I want to bring out. Are there any questions about this topic? Because this is kind of an important one. All right, so that's enough about that. We also talked about how we had a wide range of behaviors that processes could exhibit. And we talked about interactive ones where they're usually not actually doing anything because they're waiting for input. We have compute-intensive processes, which are computing, so they have the CPU and they're accessing memory. They're not doing I/O. They don't really care about what the user wants, or maybe they're carrying out what the user wants. Let's be positive, right? So they want really long time slices on the CPU. And then we have real-time processes, which need very regular but small time slices on the processor. So we have all of these general kinds of behaviors that we can see. And we talked about round-robin scheduling as shortest jobs first. So round-robin was good for compute-intensive, really bad for interactive, and shortest jobs first was really good for interactive and bad for compute-intensive. And what you notice is that when you have processes that all behave the same, it's really easy to figure out how to schedule them. Like if we only ever had interactive processes, our life would be made because we'd just throw shortest jobs first at it and be done with it. Or if we only had compute-intensive tasks, we'd basically let each one of them run as long as it possibly could until it needed to stop. That's what the old multitasking time-sharing systems would do. Run, run, run as long as you can. No context switches at all, because even one context switch is more expensive than no context switches. And when you try to do I/O, then I switch to somebody else, and that I/O can occur in the background. So it becomes really easy when everything is the same. And the problem really arises because we have this mix of process behaviors, or even processes whose behavior changes through the lifetime of the process. So that's really what makes this scheduling issue more difficult. Now the last one that I wanted to talk about, this is not the optimal scheduling algorithm for real-time processes. It's really curious, and we talk about one of the curious aspects of it in the CS124 lectures. So I'll just give you that little tease right there. But real-time processes, generally we have deadlines. So I get the CPU, and then the kernel knows I need it again in 20 milliseconds, I need it again in 15 milliseconds, or 50, or whatever my frame rate I want to do. They also tend to be cyclic, so I need to process some data. So I get a little CPU burst. We actually call them CPU bursts. I get a little CPU burst, do my stuff, and then I yield the CPU. Okay. So presumably, for example, if I say I need to be woken up every 20 milliseconds, I don't expect to use 18 milliseconds every time I get get woken up. I may use like 1 millisecond or 3 milliseconds, and then the others I spend sleeping. So the scheduler can estimate, or the process can inform the scheduler of various values. So like you see here, when is the deadline for each process? So we call that T sub DL, so that's the deadline. What is the average runtime for each process? So clearly that gives us a time, like the latest we can start if we're going to hit our deadline. And so the scheduler just looks at all the real-time processes and figures out which one is most likely to, I shouldn't say most likely, but closest to missing its deadline. Okay, by saying, I know the current time, I know how long it's going to take to run, and I'm going to compare that to the deadline and see which one has the smallest value for that. This works also if somebody misses their deadline. They'll get to go first, even though they're going to miss it. So you can see that this algorithm or this approach could easily get into a situation where we overcommit the CPU and everybody keeps missing their deadlines by more and more. So that's one characteristic of earliest deadline first. It's not ideal. Usually what happens is the long-term scheduler, i.e. the user, comes in and says, I'm going to stop trying to play so many kitten videos at once. So that's generally the way that this problem is solved, is that we just kill processes. But anyway, you have various things that you can do, like I say here as well. Minimize the average lateness, maximum lateness. One of the things that you notice about human beings is they don't care if the video plays like each frame a millisecond or two late, as long as it's pretty uniform. It's the stuttering that really bothers our brains. That's the thing that says, we look at it and we're like, wow, that is really frustrating. It's stopping, the kitten is stopping and then starting. So if it's uniformly distributed, this missing of deadlines, then we don't mind so much. And so sometimes simple schedulers will try to do things like that. Okay, so that's real-time scheduling, at least a very simple version of it. We'll talk about why that isn't so great and what a better approach might be in CS124. It's just way beyond the scope of the class and the time that we have right now. So we have this general problem that we have different behaviors and we'd like to deal with them differently somehow. So interactive processes, they should run at a high priority. We know they're going to use the CPU for a small period of time. We may have processes that are blocked on I/O a lot, but then they do more processing than just a little tiny. And they should probably be a little bit lower priority than the ones that get rid of this, get off the CPU really fast. And we have compute-intensive tasks, which would like large time slices if we're available, but if there's an interactive process, we want to preempt the compute-intensive process. But in general, we'd like it to have large time slices if they're available. And then we have real-time tasks, which need to be even higher maybe than the interactive processes. Although generally this is not a problem. Human beings do not type fast enough to make the kitten videos stutter. Okay? Just doesn't even matter if you're on Dvorak keyboard or whatever. It's just like, we're just not fast enough. So we can take our components, our different approaches, and we can figure out how to combine them in some reasonably elegant way, like we have in the past, to figure out how to build a general purpose scheduler. The scheduler that most often is used to do this is called a multi-level feedback queue scheduler. Okay? It is sometimes abbreviated MFQ or MLFQ. Depends on the operating system you're looking at. But you can see that it is used in a lot of different operating systems. Okay? I don't remember if it's used in Windows 7. I haven't updated this slide to include Windows 7 or not. So I'd have to go back and look to see if... I mean, Windows 7 and Windows 8 have done some really innovative things. It's not like I only hate Windows. Everything's got some strengths and weaknesses. Windows 7 and Windows 8 actually did some really innovative stuff with scheduling, which again we talk about in 124, but it's beyond the scope of this class. Anyway, the idea is, well, if I have these different processes that need to be treated in different ways, why not just create a whole bunch of queues, and then my queues will allow me to segregate processes based on their needs, based on their behaviors, and the queues also can represent different priority levels. So this is the premise behind multi-level feedback queues. So queues have an associated time slice and also optionally a scheduling algorithm that's associated with that queue. If you don't have a special scheduling algorithm associated with the queue, then you just use round robin because that's easy. Okay? So in general, we have these queues. Each one has its own time slice, and we can move processes between the different queues. This is the feedback part. So we look at how the process behaves, and depending on how it behaves, we move it into a queue that best corresponds to that process's behavior. Okay? And so the nice thing about this approach is that if a process's behavior changes over time, like I'm on MATLAB and I'm typing stuff in and then I run and it starts using the CPU all the time, then I'll start noticing, hey, this process is getting preempted a lot. It's not waiting on I/O anymore. It's switched into compute-intensive mode. So it starts moving to the queue that best suits that process's behavior. So it's really neat. It's a really neat idea. Really simple example. We have 3 queues, 3 different time slices, 5 milliseconds, 15 milliseconds, and 30 milliseconds. And each queue is just going to be round-robin scheduling. So the rules generally follow that if I have a new process, I assume the best about it, and I throw it into the highest priority queue. So I always give everybody a chance to really please me and impress me. If a process gets preempted, and what I mean by this term preempted, I've kind of been using it without saying what it means, but you can probably guess. Its timer interrupt goes off, and the process is kicked off the CPU by the kernel. So that's what we mean by preempted. It's preempted by the kernel because it used its entire time slice. Okay? What happens is you say, okay, you're being naughty, or at least you're not suitable for this queue, so we're going to put you down a queue level. We're going to try to give you a larger time slice, but now you're lower priority too. If a process yields the CPU in various ways, either by actually yielding it or by doing some I/O or making some kind of long-running system call, and the time slice hasn't fully expired for that process, yay, it gets to stay in that queue. Okay? But it goes to the end because it's had a chance now. So we do round-robin scheduling on the queue. Also, if you have a process that's behaving exceptionally well, and it keeps yielding the CPU well before the time slice of the next queue, we can move it up. Because now the current queue that it's in is really, it's got too long of a time constraint for this process's behavior. We can move it up and it will still behave well. Okay? So you can see that we have these simple rules that allow us to move these things around. Any questions? Yes? You're probably going to get to this, but how do you interleave these queues? How do you interleave these queues? Well, yeah, we don't really talk about that too much. We'll talk about it a little bit. We wave our hands a lot in CS24. You have to implement this in CS124, so you won't get to wave your hands. But yeah. What you notice, though, I mean, basically what you do, I'll give you the punchline, or at least as much of it as we're going to talk about in this class. What you do is you handle all of the processes that are in the highest priority queue first, round robin, and The way to think about it is if they yield the CPU because of I/O, what they do is they actually don't stay in the ready state. They end up going to a blocked queue. Okay? But you remember that it yielded the CPU, so when it comes back, it gets to go back to the queue that it was in. If it gets preempted, then you move it down to a lower priority queue. So basically, you always end up exhausting all the ready processes in a given queue. They either end up becoming blocked or they end up being demoted, unless it's the bottommost queue. And so what happens is, as you go through all the processes, you really do end up with no processes at a particular priority level that are ready to run. So you go down to the next level, and then you exhaust all of those. And you end up with all of the ready processes have been serviced, except for the ones in the lowest priority, and you just round robin those until some blocked process becomes unblocked, and you go back to the queue that it was in. And it preempts whatever was running. Does that make sense? So that's the framework that sort of ties this concept together. Anyway, so that's really cool. Like I said, you definitely get an opportunity to implement this in 124. In fact, it's Lab 3. It's the first Pintos lab, so it's fun and scary, I guess. Anyway, but yeah, the general thing here that you notice about multi-level feedback queues is pretty much instantly processes are moved to a queue that corresponds to their needs, and also an appropriate prioritization based on their behavior. So that's kind of neat. So yeah, this is just basically the long-winded way of saying what I just explained to you. The queues with shorter time slices are higher priority. So if you ever have a ready process in one of those higher priority queues, it will preempt the process that's in a lower priority queue if it currently has a CPU. So that's really nice. And then once we've exhausted them all, we end up with only the processes that want large time slices, and you just give them to them. And so they get long time on the CPU without very many context switches. Okay, did that make sense? I've never really gone into that depth, so I mean, I like the question. It's fun to talk about, but I've never really gone into that depth in here, so hopefully it made sense. Okay, so these were our queues. So Q1 ends up with processes that work in 5 milliseconds or less. Emacs would be in here. Vim would be, well, maybe not Emacs. That's a lot of work. No, I'm joking. But anyway, Microsoft Word, probably not. So, but anyway, you end up with all the processes that just do a little bit of work and then quit. So that's cool. Q2, maybe interactive, but do a little bit more work. Maybe it's that Flash game that you're playing in the web browser or something like that. And then Q3 is going to have processes that take at least 15 milliseconds. Now notice they may want the processor for a lot longer than 30 milliseconds, but they don't get it. But they also don't get demoted. So Q3 is just stuff that takes at least 15 milliseconds, and the processes in the queue get 30 millisecond chunks. Okay. And of course, if a process starts becoming I/O bound frequently, it'll get to migrate back up. Okay. Now, the thing that's really nifty about multi-level feedback queues is the fact that you can assign different scheduling algorithms to different queues. So a lot of time, what happens is a certain range of queues are devoted to real-time processes. And the scheduling algorithms are correspondingly different, because we want to make sure that we give the time slice regularly. Because they are real-time processes, they always preempt everything below. And so that way, if a deadline is coming up or a time to schedule is coming up, the real-time process will preempt even interactive processes and so forth. So they basically always get the CPU when they need them. The presumption is that they're well behaved. If it's not, the user probably won't run the program because it will really make the system unresponsive. So here are a few examples. So NT-based systems, you would have 32 levels, 0 to 15 are normal, and then 16 to 31 are soft real-time. Again, remember I talked about the difference between soft real-time and hard real-time. I think I did last time. Okay. And again, you'll notice something really kind of weird is that the level number doesn't really correspond to the priority very well across operating systems. So Windows, the higher the number, the higher the priority. On Linux, at least up to 2.5, the lower the number, the higher the priority. So I guess it's just if you like jump if greater or jump if less. Okay, so like it says here, level 0 to 99 are real time, 100 to 140 are nice task levels, so you could vary the niceness of a process, and it would change the queue that it's in. And OS 10 uses something else, and Linux uses something else. So OS 10 has something that roughly corresponds to this, but it's much more coarse-grained, and obviously it manages processes on a much more individual basis. So I think this is neat. We have this really simple API, and the API is conceptually straightforward to understand. I mean, I know that you're all new to it, but I suspect that if I said, hey, go write a command shell, you probably could figure it out without too much difficulty. Okay? Especially because you've got, like, exec VE? I can't even remember what it's called anymore. But exec VE, and then there's a whole bunch of versions of it. Like there's a version of exec called exec P that actually searches the path on the operating system for you. It's like, wow, just do all my work for me. I feel like I'm in Python all of a sudden, you know? So it's like, but you have all these tools that you can use. It becomes very straightforward to write programs that use these APIs. But you can also see that the implementation has a lot of little nuances and considerations that need to be considered, particularly in the face of differing process behaviors, if you want to have a system that is responsive and enjoyable to use. And if you happen to be really curious about scheduling, like it's a fascinating topic to you, I would download the Linux kernel source, and I would start looking at the scheduler, and you can even write your own and give it a try. And I believe that there's actually batteries of tests that you can run that test interactivity of the system and so forth using whatever scheduler you create, because they obviously don't want their OS to suck. Okay? So you can have tests that tell you if your scheduler is horrible or cool or what. Okay? Any questions about scheduling? Okay, so this is what we've done so far. We have this process abstraction that is really fundamental and central. I mean, this is why we actually spend like 3 weeks talking about it. But it's very central to the way that operating systems work. And so we had these issues that we looked at. How did we solve each one of them? So how do we enforce the differences between the kernel and application process? Well, that was easy. We'll fix it with hardware, operating modes. In fact, that was the thing about the old Assignment 8, which is dying, which is probably a good thing. But Assignment 8 was all about showing you that if you don't enforce these things in hardware, they can always be compromised. And so we really do need hardware support for this, or else programs really can't trust that the operating system will be able to enforce the constraints that we really need it to enforce. So we have hardware protection levels, hardware operating modes, and so forth. What state information do we need to manage, and how do we organize it and manage it? And we saw, okay, well, we understand what the process context includes. We have a general sense of how to save it, although we haven't cracked this nut of the program memory. Right now that's really slow because we copy it all. And we can have some kind of kernel data structure, process control block or task struct, whatever the operating system might decide to typedef the struct name as. And that's where all the context information will go. Curiously, just as an aside, Assignment 6 and Assignment 7 store the context on the stack. And that is actually the way that most operating systems work. So if you're looking at that and saying, that looks a little hinky, that we're always storing the context on the stack, that's actually the way that operating systems work. Also, how do we interrupt a running process? How do we get it off the CPU? Well, hardware timers. And hey, we'll require protected access to be able to configure hardware timers so that processes can't just go in and say, you know what, forget about that timer interrupt. I'm okay. I'll just stay on here. It's nice. I'll run forever. So we have ways of doing that. If a process misbehaves, we get a hardware exception, and the operating system can step in and deal with the process. How do we choose what process should run next? We also have at least a sketch of how that would work. We have some kind of scheduling algorithm. For 6 and 7, you'll notice that, well, we basically do round robin because we're keeping it really simple. But you can see that if you can record information about how much time the process has taken, blah, 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 then it's pretty easy to come up with a way of managing things in a more intelligent way. Most important details that we've left out so far all seem to deal with memory management. Okay? So that's the one thing that we still haven't talked about. How do we isolate process address spaces? We had this stupid I'm going to call it stupid because it's in my slides. But we had this stupid idea that, okay, well, processes can only see inside this magical area called the box in the slides. And then there's a whole bunch of other memory, and only the kernel can see it, and we copy stuff back and forth. That seems really dumb. How do we provide faster context switches? Well, if we're copying memory, that's going to be really slow. And then there's all kinds of other questions we could think about asking if we want our operating system to be more than just very basic. So how do we provide easy access for processes to call into the kernel? You know, system calls, that kind of thing. Shared libraries, that would be really nice. So I don't, like the C standard library is used by virtually every program that runs on your computer. So why do I have to load it into every program's address space? That seems dumb to waste that much memory. So we have this notion of shared libraries. I have one copy that I load, and everybody shares it. It's magic. Okay. And then we have other things as well, like shared memory between processes, so that now I can have multiple cooperating processes that communicate through shared memory. That happens to be the fastest way that processes can cooperate, because you're basically limited by the memory bus speed. So this was our previous approach, remember, the one that I just said is stupid, where we have all this memory, and only the kernel can see it all, and only processes can see within this particular region. It turns out that this is very similar to a segmented memory model, which, again, was used very extensively in the olden days of like the 60s and the late 50s and the early 70s, when people were trying to figure out how to crack this problem. Context switch, what do I do? Well, I interrupt the running program. I have to copy stuff. This is horrible already. Okay. That's going to probably be okay because some of the information is going to be in the caches. And then I have to copy another process's context into the box. That's probably going to be a lot of cache misses, so this is going to be really slow. And then I start running the new process. Okay, so lots of copying. Gonna be slow. Hopefully you saw that. I mean, it kind of blows my mind. Just as a little aside, I love the assignment 5 last problem because that data structure is just so poorly behaved when it comes to cache utilization. I mean, if you have a program like that and you can get like 1,000-fold performance improvement out of it, that's like, wow, the old version sucked. That's kind of your takeaway. So anyway, I mean, doing this kind of copying, data movement, if it's the only thing you have to use, you do it. But if you have any possible other way of doing it, you really don't want to fall back on that kind of approach. Also, we have a constraint that all of our processes have to fit in DRAM. Okay? So if I have a situation where I have certain processes that want just huge gobs of memory, and other processes that aren't running right now, maybe they're blocked, waiting on the user, and the user is ignoring them right now, well, those are still taking up memory. Okay? Or various other situations. We're going to talk about a lot of that next time because that's kind of a really important problem to solve. But you can see that we have these issues. And they all basically come from the standpoint, or from the fact that our processes, our programs, do physical addressing of memory. Okay? So you see our main memory is an array of m contiguous bytes. M is typically a power of 2, so we could write 2 to the lowercase m, as we usually do. Lowercase m is the number of bits we need to address capital M. So the program accesses memory. Instructions contain physical addresses. So I say move 7 EBX, and remember there's no $sign in front of it, so I'm not moving the constant 7, I'm moving the value at address 7. So the physical address 7 is sent to memory, and memory is like, oh, okay, let me see what's there. Well, it sends back the value to the processor. What we'd like to do instead is figure out a way of translating addresses that come out so that instead of having physical addressing in our programs, they do this thing called virtual addressing. So now instructions, instead of encoding a physical address, they encode a virtual address. It's an abstraction. The programmer doesn't care. I mean, probably none of you ever cared about virtual memory before today. But anyway, we have a virtual address in instructions, and what happens is the hardware translates that virtual address into a physical address that's used to access memory. So like you see here, we have an address lowercase a, and instead of using that directly as an address, we send it through this mapping table T, which translates virtual addresses into physical addresses. so that now we can actually change where virtual addresses actually are stored in the computer. You know, most problems in computer science can be solved by adding another level of indirection. That's just what we did. Now, of course, we don't want to do this with every single address because that mapping table would then be larger than the computer's memory because addresses definitely will take more than 1 byte. I suppose it's possible. I'd have to think about that one. But anyway, we have the issue that, you know, at least on 32-bit platforms, 4-byte addresses. Well, if I'm going to change, you know, or have a mapping table for every byte, now I need 4 bytes times 32-bit, or, you know, 4 gigs, and so I'm going to need 16 gigs of space just to store that mapping table. That seems infeasible. We also say, well, good programs are already going to be accessing memory on block, you know, in blocks or something that works well with blocks because they want to leverage hardware caches to be faster. So why don't we go ahead and divide physical memory up into pages? Or I should really say virtual memory because there's pages and page frames. Okay, so we divide memory up into pages of some size, which again is a power of 2. So capital P is a power of 2. A lot of times it's 4 kilobytes on IA32, kind of because that's what the hardware supports. And so you can see it's much larger than 1 byte or 1 word. And we map each virtual page to a physical page. Actually, we call them page frames, but we won't get into that right now. We'll talk about that more next time. So the mapping is using a page table, which maps virtual pages to physical page frames. So page table entries, basically what we do is we use the virtual page number to index into the page table, and the value at that index is the physical page frame to use. So I have some pictures. Okay, so main memory provides a physical address space and bytes. Oh yeah, so this is what we were saying before. So it's the same idea as before. This is the physical address space description. So M bytes. And you could say, okay, well on 32-bit that's going to be 4 gigabytes. It could be, if you only have 1 gig of RAM in your system, then really you only have 1 gigabyte of address space because that's all you have. Okay? But the processor still says, oh, you've got 4 gigabytes of addressable memory. Then we have a virtual address space of N bytes. M and N are not usually required to be the same, but we're going to constrain it for right now just because it makes it easy. So on IA32, 32-bit addressing, we have physical address space of 4 gigs and a virtual address space of 4 gigs. And so the virtual memory system maps virtual pages, which are pages in the virtual address space, the addresses that programs use into physical page frames, which are pages in the physical address space. Now, of course, like I was saying, we don't want to do this in software because that's a bad idea. This is already going to be scary. In fact, when people first designed this, they're like, how in the world will this ever be fast? Thankfully, they figured out a way because it's become really central to the way that operating systems provide this process abstraction. Okay, so like I said, the address translation in hardware would be slow. So there's a special component on the processor called the Memory Management Unit, MMU. And that is the component of the processor that's responsible for doing address translation. Okay? You'll notice the MMU, it takes an instruction and it says, hey, I want to access address 307. And the MMU is like, sure you do. And it goes and looks up in the page table what physical address that actually corresponds to. And then it sends off a little message to the memory saying, hey, they want address 7. They think they want 307, but that's not what they want. And so main memory sends a value back, and that comes back to the instruction. So the instruction sees what it thinks is the value at 307. Okay, everybody got that? That's the idea behind virtual addressing. There's this little hardware component that tries to do this kind of translation super duper fast. The way that it does this is very similar to the way that we do our hardware caching. We get the virtual address and we basically turn it into 2 components. The easy part is a virtual page offset because remember, these things are pages, so I have some bits in the address that just tell me what offset in the page I'm actually accessing. So that'll be bits 0 to p minus 1, the low p bits. Okay. How many ever bits you need to represent the page size. Okay. Then the rest of the value is the virtual page number. Okay, so every virtual page will have a distinct page number, and then the offsets are obviously distinct within the page. Physical addresses, again, this is why we like M and N to be the same, because you can see that the virtual page number and the physical page number are the same number of bits. The page offsets are definitely the same number of bits. We can just bring that straight across because the offset within the physical page will be identical to the offset within the virtual page. Okay, so this is what the page table does. It maps the numbers from virtual page number to physical page number. The page offset comes across directly. Okay, so this is the mechanism. We had the page table, and it really is a table. There are other ways of doing this that have been explored. There's actually like tree maps and hash maps that have been used for doing this kind of address translation. There's some really wild approaches that have been chosen. We talk about a few of them in the OS class, okay? Because you can actually have some weird kind of hardware hash map that the hardware tries to access, and if it can't find something, it generates a fault. It says, I can't find it, and you have to go set it up for it. Okay? But anyway, the table is really simple. We just take the virtual page number and use it as an index into an array of entries. And so the index tells us where to look, and the value at that index is the physical page number that corresponds to that virtual page number. The way that we control what the table is or where the table is that there's a special register on the processor that says, this is the page table to use. Now the cool thing about this register is you don't set it just once. This you can set whenever you want. If you're the operating system, if you're the process and you try touching it, you'll explode. But if you're the OS, you can set it whenever you want. And so this is really neat. You can now use this to configure and modify the address spaces of processes as they start, as they run, and as they terminate. So we abbreviate that PTBR, by the way, because it's the page table base register. This is what it happens to be called. That's not entirely accurate. That is its name in the IA32 documentation, but it's also called control register something. I think it's control register 3, but there's like 6 control registers that do magic on your processor, and one of them is the page table base register. Anyway, let's see. So yeah, instead of copying around the memory for each process, what we do is we give each process a page table. Is that page table in the process's memory area? Well, kind of, but we don't allow processes to access it directly because we don't trust processes to access that directly. Instead, the kernel gets to access that. It's part of the process's details that are in kernel memory that are not available for the process to access, but obviously have a very important effect on how the process runs. But anyway, yeah, sorry?
Just to check, but to access memory and to go to the page table virtualization, you don't need to context switch to the kernel for that.
No, you don't actually context, that's a really good question. You don't context switch into the kernel just to perform a memory access. That would be horrifyingly slow. Yeah. Basically, the way the MMU works is you set it up, and it does as much as it can on its own. That's the idea. You configure it, it does its thing, and as long as there's no problems, everything goes without any. So you never switch out of, protection ring 3, for example, if you're in an application. The virtual to physical address translation just happens on the fly. It is probably the fastest hardware and definitely the fastest caches you have on your processor, this address translation, because memory access is already slow. And if you're talking about an L1 hit being 3 clocks, well, that includes the virtual to physical address translation. It's got to be fast. So we'll get into some of the details of that next time too. Anyway, so yeah, good question. So instead of copying around the memory for each process, now we're going to give each one a page table. And you can see how these are mapped to physical frames. So the column of boxes on the right is physical page frame. The way I like to think of it is if you had a nice big empty wall in your house, which we do right now, and you have picture frames. And the picture frames can be empty or you can put a picture in them. And you have a stack of way more pictures than you have frames. And so you just sort of say, well, these are the pictures I want to look at the most right now. You put them in the frames. The other ones, if you really want to look at them, well, you got to take a picture out of a frame, go find it, and then put it in the frame. Same idea. Same principle as the way virtual memory works. Okay, so now we have page tables. Programs use virtual addresses, so they have no idea as to the actual physical layout of their memory. And in fact, nothing really affects the process as far as where its physical memory is laid out. The process just doesn't care at all. It's completely agnostic. But they do have their own address spaces because no two page tables map virtual pages to the same physical page. That would cause a physical page to be visible to two processes. Okay. So each one references its own set of pages. And guess what? Now contexting switching, I can't even talk. Context switching is a lot faster because all we really need to do is just change the page table base register to point to the new process's page table. And it's like you change one register and magically, boom, the virtual address space changes from one process to another. Everybody got that? It's totally awesome. Still, context switches are slow, okay? Those numbers that I gave you before, those are still the real numbers. Because even this is going to be slow. Because when we switch, now I have to flush all my hardware caches because guess what? They're out of date. Now the virtual address space has changed, so I need to start, when I access things, the cache data is invalid. I need to load something else. Okay? So you can see that there's some challenges. So context switch is still slow, but way faster than copying. There's a lot of different things that we get out of this. Like I said, the virtual memory layout is contiguous because that makes it easy to write programs. But the physical memory layout does not have to be contiguous. So if our instant messaging client needed more memory, I don't know, because maybe somebody sent you a picture of their cat and they wanted you to see their cat, then, okay, now the IM client needs to allocate space so that it can show this cat picture in the client. Well, now the client can just call into the kernel and say, hey, my memory heap needs to grow. And the kernel says, all right, I'll give you a few more pages for that. And so it picks some more physical pages that are available. They may not be contiguous with the other physical pages. But in the virtual address space, they are contiguous. So the client doesn't care at all that these pages are somewhere else. It just sees that its virtual address space has grown. Okay. That's pretty neat. Okay, so that's one option. Another thing. I mentioned that we don't want to have two virtual pages referring to the same physical pages. Well, what if we sometimes do? We can actually do some really clever stuff with this. I was mentioning shared libraries. Instead of requiring a shared library to be loaded once into each process's data, so that I am consuming a huge number of physical pages for some library that everybody happens to use, like the C standard library, which is big. What I can do instead is load it once. And then when other programs want to refer to it, I just map those pages into that program's address space. Now, clearly, I need to be clever. I need to not allow the program to write to them, or else it affects everybody. But I can make it read-only. We can add that. So that's one of the things we'll do. But we can go ahead and share information that is needed by all processes into every process by just mapping those physical pages into everybody's page table. Also, programs can collaborate now more easily because we can just, and obviously the way that this is done is all the programs that are collaborating must decide to collaborate if we're going to have this process isolation abstraction. So in this case, the web browser and the text editor both have to decide, yeah, I want a shared memory. And then the operating system kernel can assign some page table entries that point to the same physical pages, and now that is shared memory. When one program writes to it, another program looks at it, it's going to see the same physical page, so it'll see the data that the other program wrote. Okay, any questions? It's really clever, nifty stuff. Take CS124, implement these things yourself. You'll have so much fun. You'll be happy when it's over, I'm sure. So anyway, you can see that we have a lot of things that we've already achieved. It becomes a lot easier to manage memory and processes. So now we know our context switches are fast. It becomes really easy to hand over memory to processes on an as-needed basis. We don't care about keeping things physically contiguous. We can just assign whatever physical pages are necessary. And processes have a literally, truly isolated address space from each other because the page tables are separate. We can configure them however we want because we're the OS, and that will control and constrain what processes are actually able to see. So that's really nice. And we can also have this nice shared memory abstraction. Now, we still have the problem that I mentioned before that we have to actually share our main memory, which may be limited. Like I said, what if we have an old system where we only have 1 gig of RAM? Probably highly unlikely. What's like? How much RAM do people have on their systems? 2? Does anybody have 2 gigs? That's what I'm thinking. 4. I'm seeing a few people with 4. Who has more than 4? Wow, like 3/4 of the people here. So like 8? Is it 8? Anybody have more than 8? Okay, is it 16? Okay, anybody have more than 16?
My dad.
How much does your dad have?
64.
64. Okay, yeah, I know a few people who have 64 or more gigs. It's usually for compute nodes that need to be able to do a lot of crunching. Yeah, in-memory databases turn out to be super fast. If you don't have to touch slow disks, it turns out they're really fast. So anyway, we have this issue that we have a certain amount of physical memory that we have to share amongst all of these processes, and that's really annoying. It's just like we were talking about last time. What if I'm writing my hum paper and I realize that writing a hum paper is way more boring than anything else? And so I decide to minimize that program and start working on other things. Why should that text editor still be occupying any memory at all in my computer? It is. So we need to figure out some solutions for this. So what we do next time, we'll get to actually stop a few minutes early, is we'll start looking at this from the perspective of our memory hierarchy. DRAM is a cache for the disk. And if I can do this virtual to physical page addressing in DRAM, why don't I start moving some data that I don't care about to disk? And then that way, I'll free up more DRAM for programs that actually want to use it. So we'll go ahead and extend this concept, and it becomes even cooler if it's possible to believe. Okay, so we'll see you all next time.